experiment we performed in the wind tunnel. This is going to be the aerodynamic effects of body kits and closed windows on vehicles. Our group members are Rana, Katherine, Robert, Ken, and Nick. The scope of our presentation today includes first the history and purpose of body kits. Next will come the aerodynamic theory behind these body kits, the testing processes we used, as well as the devices, parameter optimization, results, followed by a discussion of the results and a conclusion and recommendations. Body kits refer to a modification of the shape or style on a vehicle. The first aerodynamicist for vehicles was Jim Hall. He started studying the effects of body kits in the late 1960s, and building began in 1970. It was primarily banned by F1 because of potential disadvantages, but the big boom of body kits came on the streets in 2001, and it's used in streetcars in Japan. The purpose of these body kits are to reduce race times, as well as provide a smoother ride and prevent lift, and they are also used for aesthetics. As you can see on the picture, there is a body kit attached, which is actually producing a downforce on the vehicle to prevent lift along fast turns. Body kits consist of anything with a rear spoiler or a front and rear bumper, as well as side skirts. Lamborghini doors can be seen in the top right picture, hood scoops, and fender flares. The effects today we're going to study are the front bumper, which you can see in the bottom right picture. Body kits started in the 1960s, and you can see in the pictures their rear and front spoilers. In the 1970s, body kits progressed, and they brought a larger increase to the hood scoops and more extravagant front bumpers. The 80s and 90s kits showed higher importance on side skirts with smaller rear spoilers. Car companies have created drastic front bumpers nowadays which allow airflow. Hood scoops and side skirts are designed to be sleeker and less dramatic. Rear spoilers have stayed relatively small, even being mechanical with the option of being fully hidden. Today's body kits are aesthetically pleasing to the eye. Next will be the aerodynamic theory behind the body kits.
Okay, so we have some theoretical equations here. The important parameters including drag force, drag coefficient, pressure coefficient, skin friction, and the Reynolds number. Features more streamlined bodies, for instance like the side skirts, front and rear bumpers, fender flares, decreased drag, and pressure coefficients. The spoilers increase downforces and prevent the lift, and paint jobs can also decrease skin friction. So for our experiment, the objective was to determine the effects of front bumper body kits and to determine the effects of windows rolled up or down, both to be tested at low and high speeds. The procedure included 4 different types of styles of cars. 1, no kit, and windows down as our test model. No kit and windows up, a kit and windows down, and a kit and windows up. The front bumper and windows were made from styling clay. Each test is in a wind tunnel at 5 different air speeds. So here's some of our testing bodies. Our black car, as you can see, has no kit and the windows are down. The green car has no kit and the windows are up. Next, the pink car has a kit, but the windows are down, and the yellow has a kit and has the windows up. Here are some of our testing devices. Low-speed wind tunnel, load cell used with a manometer, and the Velcro attachment. So our testing procedure went as follows. We, the wind tunnel turned on, pressure bias recorded. We set the speed for the wind tunnel, the odometer reading. We recorded the odometer reading. We recorded the load cell for the fixture by itself. And the first car was placed on the Velcro fixture, and the recording was read from the load cell. And we just repeated these steps for the remaining vehicles and for the remaining speeds as well. And the questions we had for ourselves, can these body kits provide any improved performances? Won't increasing the surface area of the car cause an increase in drag? Are the body kits beneficial at all speeds? Do roll-down windows actually cause excess drag? And do they at all speeds? Our expectations were as follows. We thought that the rolled-up windows would provide better aerodynamic performance, but only at high speeds. We also hypothesized that the selected body kits should create a more streamlined body, lowering the drag coefficients at all speeds.
I'm going to take a look at some of our results. The first test, we had a velocity of 13.65 meters per second. As you can see, the black and the pink cars had much lower drag coefficients than the green and the yellow. The green and the yellow both had the windows rolled up. The black and the pink both had the windows rolled down. This may be because entrainment, where the air leaving through the back window does not allow for a large wake region to form on the back end of the vehicle. Also, skin friction. Cars with the windows rolled up experienced a significantly higher drag coefficient. For the second test, the velocity was measured at just over 32 feet per second. As you can see, the black and the pink drag coefficients were still significantly less than the green and the yellow. However, the green and the yellow had decreased significantly. These results were very similar to the first, but the cars with the windows down performed much better. This was a slight improvement with performance. The black, green, and the yellow cars all did pretty well. But the pink car only had a 4% increase in CD, and the yellow car still came in last place. The third test, the velocity was increased again to almost 51 feet per second. This time, however, the pink and the yellow cars, both with body kits, had drag values that were much smaller than before and actually better than the black and green vehicles without the body kits. As you can see, the drag coefficient for the pink car went from 0.71 down to 0.547, and for the yellow car, 1.02 down to 0.66, whereas the black and green cars showed values slightly larger than the pink and slightly less than the yellow of 0.625 and 0.651. At this point, all the vehicles exhibited similar drag coefficient values. At moderately low speeds, the body kits with the windows up still experienced a larger skin friction along its surface.
Okay, for the fourth test at 69.2 feet per second, the pink car is still performing better with a CD of 0.456. The black car is not doing as well as previously with a 0.537. Green car did significantly better with a CD of 0.518, and the yellow car performed much better with a 0.47. And this is because the body kits start to display characteristics of a more streamlined body due to the delay of a turbulent boundary layer. And for the final test at a wind speed of nearly 87 feet per second, both the pink and the yellow cars performed significantly better than the other two without body kits, with the pink car with a CD of 0.415, yellow was 0.46, green with nearly a 0.55, and black was 0.575. Now these results are similar to the ones in the fourth test run, mainly due to the effects of the streamlined bodies provided by the body kits. So here are the results, which represent the Reynolds number. The Reynolds number for the black and green cars do not differ due to their surface, their cross-sectional area is the same. As well, due to the presence of the extended bumper, the pink and the yellow car also displays similar Reynolds number at the varying velocities. Below are the graphs of the Reynolds number plotted against the drag coefficient. Now all of these start to level off about the third run, but the graph on the right-hand side is a close-up of the last two runs, and you can see a drastic improvement of the cars with the body kits attached rather than the black and green with no body kits. So windows up or windows down did not seem to matter as the speed was increased. Now it's important to discuss why these changes happen between the different modifications. With windows down, there offers the advantage of the car to exploit the phenomenon entrainment. Entrainment is a suction when airflow is pulled close to the body due to an internal region of low pressure. There exists an inflow through the side windows and an outflow through the back window. In the cabin, there is a pocket of circulating air where a small amount is being pushed out through the front side windows by high pressure and then pulled back in further along the body into the back side windows by low pressure, caused by the faster moving free stream outside due to a laminar flow sticking to the body. The air leaving through the back window does not allow for a large wake region to form because there is an outflow in the back vehicle. So the vehicles with the closed windows experience larger skin friction and pressure drags at low speeds. Because the flow remains laminar along the body for the vehicles with body kits due to entrainment, the airflow near the surface does not differ too drastically from that of the free stream. As a result, the boundary layer experiences little displacement, which in turn translates to a small momentum thickness. Vehicles with the windows up will experience a large skin friction drag, primarily due to the increased surface area which the side windows occupy. These vehicles also experience a larger wake region in the back due to the separation of the flow and the velocity difference in the air than in the wake and then in the free stream. So the pink car, which consisted of both a bumper extension and windows down, performed exceptionally well at both low and high airspeeds. So with the modification of a body kit, it is hypothesized that the airflow will be forced to flow along the top of the body, remaining laminar longer and delaying a turbulent flow than traveling underneath the vehicle with the absence of a body kit and losing magnitude of the airflow due to a large clearance from the ground.
The conclusion of our experiment today can be separated into two speeds. At low speeds, the windows up showed to have a high skin friction drag, which was not beneficial to the vehicle's total drag. At high speeds, the body kit did manage to minimize the drag coefficient. Throughout this experiment, the pink car proved to be the most aerodynamically efficient, having the smallest coefficient of overall drag. The pink car was the car with the windows up as well as the body kit attached. Recommendations for the experiment include changes in procedure and setup of the experiment. In an open windows case, closing the back window to create a more real-world problem would be beneficial. In the case of our experiment, the air could flow through the vehicle. With the back window closed, potential increase in pressure drag would occur. Another recommendation would include adding a ground platform for the vehicle. As opposed to going underneath the vehicle, air will be forced along the surfaces of the vehicle, which could then be considered more of a streamlined body, and again is a more real-world problem.